Welcome to the second lesson of Module 2, that is analyzing graphs of polynomial functions. I hope you watched the videos of lesson 1 where we discussed about polynomial functions and power functions. Now we will analyze graphs of polynomial functions. The learning objective of this lesson are approximate zeros by graphing polynomial functions, find extrema of polynomial functions. We will be thorough with these two objectives in the coming videos. We will solve plenty of problems for these objectives. And few of the key words in this lesson are zeros, polynomial function, and extrema. You might have come across these keywords before as well, but anyways, you will be coming through this in this topic. Now, let us introduce ourselves to the location principle. Let's see this figure over here. You have a function like this, and you can see point f of a at a distance from 0 and f of b that is at b distance from 0. There are 2 points. You can see one is below the axis, x-axis, and one is above. You might know by now, over here, the function value of the function will be negative because it's down. Over here, it'll be positive. Why? Because it's above 0. So it'll be minus, say it is minus 1. This is minus plus 2. What does it tell us? The location principle says that whenever you have 2 points of function, if one of the point if 2 points are of opposite sign, see this is of negative, this is of positive, then there is a 0 in between them. Why? Because it will cross, right? It has to cross from minus to plus or from plus to minus. So it has to intersect the x-axis, and this x-intercept is the solution. So that is what it says in simple words. So this is the proper definition you can go through. But if you understand the concept, it is more than enough. Even if you extend this, then consider 2 points over here and over here. You will have positive, negative answer. And then there will be the solution. There will be a 0 between these two values. That is the location principle. Let us solve a simple problem on location principle. Determine the consecutive integer value of x between which real zeros of f of x, this is the function over here, is located. Then draw the graph. Now you have to find out the zeros. You can't find the exact zeros. You need to approximate where do they lie. So what you need to do is you need to make a table of values. See, now over here, based on the degree, since this is a fourth degree polynomial, you can have maximum 4 real zeros. Or it can be less than that, but maximum is so much. If it is, say, x to the power 2, in some cases you will not have any real zeros. See, now if the graph is like this up above, you'll only have imaginary zeros, no real zeros. It's 0. I mean, there is no solution for this. But how many maximum solution it can have is only 2. See, like this, it will cut only 2 times, not more than that. Now since it's x to the power 4, it can have maximum 4, but it may be less than that as well. Okay, so now we will do table of values. We will assume some values. Say over here minus 2, minus 1, 0, 1, 2, 3, 4 are considered. Substitute it over here and solve. How do we find this? Now I'll just solve 1 over here. So what you have to do is you need to substitute this x value instead of the function x over here. The variable x is there, right? Instead of that, substitute the assumed x value of minus 2. Minus 2 to the power 4 minus 2 multiplied with again minus 2 the whole cube, and minus again this minus and bracket minus. Remember, x is considered to be minus 2. So make sure wherever x is there, put minus 2 over here. Square plus 1, and the answer is 29. Same way, you need to change this value. Now don't press on, just in your exam, just change it over here to 1 instead of 2. Let the brackets be there as it is. Just change this to 1. It is very easier. And now you can find the next answer, that's 3. Similarly, you can change it to 0, 1, 2, 3, 4, and you can find the answers. So now from here, you can see the sign f of x, the value of the function, changes sign from where to where. From 0 to 1, it is positive, negative. And again from 2 to 3. So from the location principle, we can say there are zeros between 0 x value of 0 and 1, and also in between x value of 2 and 3. So that is the location principle zeros. So now sketching the graph is very simple. You have the table of graphs, table of values, and now just sketch the graph. At -2 over here, it is 29. At 1, -1, it's 3, and so on. Take a proper scale and you can easily graph it. At -1, over here is -1, it is 3. 1, 2, 3. At 0, it is 1. At 1, it is -1. At 2, it is -3, and so on. You can see this is the graph. So this is how we can easily graph it. The next topic is extrema of polynomials. Now, extrema, as you can see, is something extreme. It can be a relative maximum or minimum. It either is topmost or bottommost, extreme points, as you can see over here. Now, this graph is like a cubic graph. It will extend forever. So don't see the last parts. See this part, the minimum most point comparatively. So it's called relative minima. And over here, this is relative maxima. As you can see, point A is relative minimum and relative maximum point is B. So these both points are extrema. Again, I repeat, please don't see these points, the line where it extends forever. And these are also called turning points. Why? Look, the graph over here was going downwards and it turns and moves upwards. See, decreasing, and over here at point A, it increases and again decreases after point B. So they are also called turning points. Now, how many of these turning points are there? Or extremas are there? Now, if you have a parabola, let's say this is x to the power 2. Now, what happens is, you can see there is only one. Now, over here it's cubic, there is 2. If you go to another like this, x to the power 4 graph, it might be 1, 2, 3. So this is x to the power 4, okay? What you can see is, if the degree is n, that is any number, n minus 1 will be the maximum utmost. Utmost is maximum extremas. It can be less than that as well, but it can be only maximum up to n minus 1. Now we will see a problem over here. Identify the extrema. We have this function. We need to use the table and graph this and estimate the x coordinate at which the relative maxima and relative minima occur. Now, it's very simple. You need to make a table of values. So what do you do in the table of values? Take some random values. Now this is a cubic. You can see it's cubic graph. So x to the power 3 is the degree. So take values from some values less than 0 and greater than 0 and find it out. Now all you're doing is, we just did this in the last problem. The same thing is repeated. So I won't go again and again, but you need to try it. Pause the video and try it by yourself. Put over here -4 instead of x. Now, if you just put -4 power 3 and -4x power 2 and so on, you will get wrong. You need to use the brackets when you solve, okay? And over here as well, -4 the whole power 2 -5 multiplied by -4, and lastly we have -2. Use the brackets, otherwise you won't get the correct answer. If you put this exactly in the calculator, you will get -30. Then just change the 4 to 3 and find the other values. So now you will get the function, the values for this function. From here, you can understand that there is negative and positive values. These are the changing points. These are the uh, we had seen this location from the location principle. These are the solution points. Over here, the solution exists. But anyways, let's see the problem now. See over here, -3, that is -1, -2, -3 to -2. You have the solution points over here. But now they have not asked you this. But if at all that was asked, this is how we solve it. It's always good to know. But now what do we want? We want the maxima and minima. So see, it goes up, it goes up. Then you can see over here there is a turning point. That is this somewhere over here. So the extrema, it's around, the maximum value. See over here from this table, you can just check which is the maximum point. Minus 30, minus 5, 4, 3, minus 2. See, this is one of the relative maxima, isn't it? See over here, this, where is it? Minus 2, f of x. Why is 3 not maxima? Because in the graph, we can understand, from the graph, we can understand this is x to the power 3. So there is two turning points. Now, you're not taking x3. Why? Because this is going towards infinity. This doesn't matter. This is not the maximum. This is not relative maximum. This is relative maximum. That is at around x minus 2. It is not accurate, but around x minus 2. If you want accurate, you can even start plotting zero point 0.5 and you can see 0.5 would be more accurate, minus 2.5. Sorry, minus 1.5, I'm wrong. It's minus 1, 1.5 would be the maximum. Now, what about the minimum point? Minimum point is accurately over here at 1. So that is the minimum point. So this is the maximum and minimum point. Over here, you can, I mean, it's asked to estimate, it is not find the exact maximum or minimum point. So these are the estimated values. So now depending if this comes in the MCQ, depending on the options, after graph, look at the options. If the graph is given, it's very simple to find. Otherwise, look at the options and solve. I hope you remember the table of values. We have already done this. This concept is very important and we have to do it many times. Now over here, we have another problem. The total number of certified pilots in the United States is approximated by f of x equals this whole function. It's a huge function where x is the number of years after 1930 and f of x is the number of pilots in thousands. Graph the function and describe the key features over the relevant domain. What this means is they have given this function and told from 1930 this function can be modeled from 1930. If we make a table of values, now we will generally make a table, say it's from 0 year, 10, 20, 30, 40 and so on years, right? But you must understand the zero. What is the zero? Can anyone think? Take time, think and understand. In this context, this 0 is 1930, year 1930. What about this 10? X is in years, right? Sorry, over here. X is number of years, isn't it? 10 means 10 years after 1930, that is 1940. And so on. You will go to the next years. So if you sketch the graph over here, so though we write 0, you must understand this is since 1930. You can't take the domain 1930 at once, it will be too much because this is, see, x is years after 1930. If you're taking 0, it's 0 years after 1930. Then 10 means after 1930 and so on. See, this is how it goes. So if you find, you can understand the number of pilots started increasing after 1930 until over here. Then they went down and then again they went down. So that is the graph, approximate graph, okay? The domain and range are all real numbers because you can put any function, any value over here and you will get an answer, isn't it? But no, this is not the case. See, over here there is domain and range, but in reality, you must understand what is the x value. It is after 1930. So the relevant domain will be only values after 1930. You can't take and predict anything before 1930. That is the crucial part over here. Because they have mentioned it's only after 1930, it should be values only greater than or equal to 0. But this is very important. X is after 1930 values, 1930 year. And similarly, which is the least value at 0? It's 7.7. So there can't be any values less than that. So the starting value is 7.7 and it's greater than that. See, is there any less value? No, because this goes on upwards. So this is the concept over here. So if you mention this, it's enough x, but the domain will be greater than or equal to x, okay? Because you can't go negative left side, and the values of y is always greater than or equal to 7.7 in this particular case. So that's the thing, and they told to find the extrema. Now, what about the extrema? Extrema over here, you can see, is somewhere over here, right? So that's about 50 years. Now, they have told 1980 and 1990. Why? Because if you look closely, it is after 50 and less than 60. See, it's somewhere over here, isn't it? 50 years means, over here 50 means, it's 50 plus 1930, that is 1980 and 1990, in the year 1930 and 1980 and 1990. So that is maxima, and minima is over here. Similarly, add 80 to this. It will be 2010 to 2020, say the least. So this is the minimum point. And end behavior, as you can see, as x is going towards infinity, this also goes towards infinity. Okay, that's the end behavior. And now you're not going to take the left side. Why? Because that is not in the domain. You cannot use this equation for the left side. It's only for the right side values. And now over here, there is no x-intercept. Why? Because if we go over here, is there any f of x 0 over here? No, it does not touch the x-axis. It's little more, right? So there is no x-intercept. X-intercept is the value that touches the x-axis. Okay, it's only the y-intercept there is at 7.708 that we found out in the table. And this has no symmetry at all. It is just there's no symmetry. It's not same both the sides. See, it's just like this freehand graph. So this is the answers. So, sorry, let me stop over here for now. So this is the type of problems about relative maxima, minima. I hope this is clear. Try to solve similar equations. The most important thing over here is always this table of graph. Okay, sorry, table of values. From this, you can graph it. And then you can easily find the maximum, minimum value, and you can understand what it is based on the question. Over here it is values more than 1930 and so on. So if you have been already given this table of values, you have to just graph, or if the graph is already given, then it's well and good. Then you can easily find the extrema, intercepts, and behaviors. In this example problem, we are supposed to use a graphing calculator. But let us see the method how it is done more than completing this problem, because many of you do not use graphing calculators. So let's see how it is usually done. Let's see what are the methods and the steps involved, and let's see what is the main concept behind this problem. The table shows US backpack sales in millions of dollars according to the Travel Goods Association. Make a scatter plot and a curve of best fit to show the trend over time. Then determine the backpack sales in 2015. So we have a table which shows all the sales in millions of dollars for every year from 2000 till until 2014. But 2015 is not there. We are supposed to estimate it. So now for the solution, basically if you want to get a graph, you can directly enter it in the graphing calculator, and then you can use the scatter plot list and you will get this graph. If you even plot this accordingly, see, the thing is you should not plot from 2000, like consider this as 0. Okay, 2000 is 0, 10 1 is 2001, and so on. Then plot it accordingly with the proper scale. You will get the graph. Now, once you have the graph over here, now determine the polynomial function of best fit. This is basically done in the graphing calculator itself. Over here, this will, based on this graph, it will tell you which is the graph, what is the function of the graph that will fit in this. So in manually, it is not possible. You need technology for this. That's why it is technology to model. Now, what happens is x to the power 4, that is a quartic function. X to the power 4 is called quartic. X to the power 3 is cubic, x to the power 1 is linear, and so on. So this is quartic. X to the power 4. These coefficients will be given from the graphing calculator. You can see over here, this is the thing. Now, graph and evaluate regression function. Now, basically, for x is equal to 15, you're interpolating. So, they are asked us till 2000, they have given the values till 2014. They're asking you to estimate what is next. So, the interpolation will be done from the calculator itself. If you extend the graph, see, it's going like this. If you extend it, you'll get an approximate answer. The answer for x15, that is 2015, is 3.523 billion. Let me just go back quickly over here. See, it was 2255 for 2013, 2014 2779, 2015 it was 315 and something. That is approximately correct. So, sorry, over here 3.523 is that is approximately correct answer. Similarly, let's do one more problem. This is about finding the average rate. This is important because there are various methods to find the average rate. We will see one by one. The RSV rocket was designed to carry as much as, I'm sorry, this typo error, as much as 75 tons of supplies and 4 astronauts to the moon and possibly even to Mars. The table shows the expected G force on the rocket over the course of 200 seconds launch. So now we have the times are given and the acceleration, that is G force, is also given. And we have to find the average rate of change. Okay, and we need to interpret these results. This result. So now first thing is optional to graph. Okay, you can graph this because we'll understand how the graph is. Now it is not compulsory to graph this. You can even find the average rate of change just by the values over here. But by graphing, let's just double check it. Now, when you graph it, you will get this. See, from 0, it is 1.34 to 20, it is 1.26, and so on. You will get this points. Now, rate of change is always dy by dx. What is dy? Difference in y. See, sorry, it's somewhere over here. What is this distance dy? If you see, it will be somewhere over here. This is 1 is 0.5 and 0.5 nearly to 1, but if you look closely, it is about 0.9. Okay, the distance over here from year to year, it is about 0.9, near to 1. And what is dx? Dx is from year to year. This is 200. Very simple. So you just divide dy by dx. That is the rate of change, the slope. So it's 0.9 divided by 200. This is your answer. But if you want to find algebraically, you need to find, see, they have told over the course of 200 seconds launch. So the final function is 200. So this is the formula, f of x2 minus f of x1 divided by x2 minus x1. This was there in the last term. We had even the problems for the final exam. In the exam scheme, we had this problem. So remember, f of x2 minus f of x1, initial value, last and initial. That is f of 200, function value of 200 minus function of 0 divided by 200 minus 0. It's, if you might remember this, y2 minus y1 divided by x2 minus x1. This is it. Now, what is the y2 value? It's 2.2 minus y1, 1.34. X and y, isn't it? So, divided by x2 is 200 minus 0. Now, you will get 0.0043. It's almost similar. So, interpret the results. From 0 to 200 seconds, the average rate of change acceleration was increase. Okay, why? You can see over it's increasing, is it? Okay, though it's decreasing over here, from this to this, the value is positive. If it was minus, then it would be reducing, but it's positive, so it was an increase of 0.043 g-force gs per second. So this is the average rate of change problem. Graphing is optional, but it's better to graph. You'll understand. But it's all depending on the time. If they have not asked it, if they just ask these two, just solve it directly. Okay. So that's about the second lesson. It is again a simple lesson. It's about graphing, more into graphing. So you need to be quick with the table of values, and then after table of values, just graphing. So try your best. Go through the videos again. If you have any doubts and if you have any questions, you can always leave it in the comment section, and I'll try to get back to you as soon as possible.